complex environment. So yesterday we talked about possibility results, what simple auctions can do. Today we're going to talk about what they can't do, so impossibility results. Now we had a pretty exciting and adventurous afternoon yesterday, so you may have forgotten what we were talking about. So let me just remind you briefly what the setting is. Exact same setting as yesterday. So we're thinking about markets with indivisible items. Okay, so M items, N bidders in the market. Each bidder has a private valuation. It specifies their value for each of the 2 to the M possible subsets of items that they might receive. Remember, M is the number of items, and so each bidder in principle has 2 to the M private parameters. And so that's why we're not discussing direct revelation mechanisms. We're discussing simpler mechanisms with relatively small message spaces. Okay, so quasi-linear bidders, and again, we're focusing on the objective of maximizing social welfare. So in a perfect world, this is what we wish we could do. The question is, if you look at the equilibria of simple auctions, how close are you to the benchmark of the maximum possible social welfare? Okay, so that's the setting. We talked yesterday about what auctions are actually run in practice, and they're kind of bells and whistles built on top of simultaneous ascending auctions. And we talked about the pros and cons of simultaneous ascending auctions. And remember, there are these two kind of folklore beliefs, and there's a rough consensus among practitioners who work in the trenches of spectrum auctions that a rough rule of thumb of when simple auctions work well. So if there's no strong complements between items, there aren't strong synergies, so it's more of a substitutes environment, then the thinking is that simple auctions, while not fully efficient, there are issues like demand reduction, while not fully efficient, still they seem to do pretty well. They seem to be near optimal. Well, but on the other hand, when you do have strong complementarities between items, then the rule of thumb is that actually simple auctions can perform quite poorly. Is there a question? Right, so that's a good question. I mean, in some sense, you can look at the types of bundles that the bidders assemble in the auction. But, I mean, they have various heuristics for doing so. But to be honest, I think this is still sort of an open question. In practical spectrum auctions, are the preferences, does the substitutes aspect dominate more strongly, or does the complements aspect dominate more strongly? They're clearly both there. But I've heard different opinions about from experts about what real life valuations look like.
The simplest example is that you just want coverage, national coverage
for a complement. Yes.
Gives you complement.
Yeah. So definitely both effects are there for sure, right? So you'll have 2 different licenses that cover exactly the same region and just happen to be different frequencies. Those are basically substitutes, and absolutely the bidders do tend to want some kind of statewide or nationwide or what have you coverage, which is a complements effect. For people who work in this, I mean, one thing I say is that, well, given that the auctions seem to work pretty well, that would suggest that it's largely the substitutes effect is dominant. I'm not sure how convincing that is, but those are the kinds of things that people say. Okay, and so yesterday was all about translating the first folklore. So again, just the high-level point is that there are challenges in making these precise, which I would speculate seems to have prevented the traditional economic literature from sort of tackling them head-on. Challenge 1 is that translating these into mathematical statements necessarily, it would seem, involves approximation, which is not really in the economic tradition. And second of all, we're talking about environments where we have no idea what the equilibria look like. So that necessitates a different toolbox than the standard economic equilibrium analysis toolbox. And theoretical computer science, as it happens, has a great toolbox for translating these into mathematical statements. Yesterday we focused on translating the first one. Today we'll focus on translating the second one. So again, just to remind you what was the culmination of yesterday's lecture, we had a formalization of the idea that when there aren't strong complements, simple auctions do pretty well. What did without strong complements mean? It meant an assumption on bidders' preferences, the valuations, so a submodularity assumption. What it pretty well meant, it meant you got a constant fraction, namely this magical number of 63% of the maximum possible welfare. And again, remember, this is uniform even as the number of bidders and items grows large and even ranging over all product distributions. We're talking about Bayes-Nash equilibria. So that was the culmination of yesterday. And again, the point of today is to say, okay, how about an impossibility result with more general preferences, with complementarities between items? Could it be that in a provable sense, simple auctions defined in some reasonable way, actually cannot achieve these kinds of welfare guarantees. And we'll see that the answer is yes. And again, it's going to be sort of the theoretical computer science toolbox that gives us the tools needed to have such a result. Okay, so that's the recap. Any questions just about so far? Okay. So for the next 20 or 30 minutes, I'm going to give you probably the world's briefest ever introduction to a field known as communication complexity. So this is a core topic in theoretical computer science. It has a lot of deep questions, but actually also has a lot of applications, and so including ones to auctions, which I'll tell you about today. If you want to know more, the Bible of communication complexity was written by Noam Nissan here at Hebrew U, along with Eyal Kuchelevitz. And then also, I recently published some lecture notes which focus much more on the applications of communication complexity, including the ones I'll tell you about today. Okay? So like most things, this is best understood beginning with an example. Oh, I should say actually. So, for these next 20 or 30 minutes, it will not at all be clear what this has to do with anything else that I've been talking about in these two lectures. So just bear with me. I promise you by the end of this lecture, we'll use these tools to make precise that second folklore belief. The second thing I should say is, the mathematical arguments we'll see, while extremely simple, may feel a little alien. They may be a little different than the kinds of arguments you're used to from your economics courses. But again, it's sort of undergraduate level stuff. So please stop me if anything doesn't make sense. Even though it may seem very foreign, you should be able to understand everything I say in real time if I do my job. Okay? All right, so here's an example of a communication problem. So Stephen yesterday was talking about Anne and Bob, two parties. In computer science, it's traditional to use Alice and Bob when you have two parties. Okay? And so suppose you have Alice, you have Bob, and they each have in mind a number. Okay, so Alice has in mind a number X, unknown to Bob. Bob has in mind a number Y, unknown to Alice. Alice and Bob want to understand whether or not they're thinking of the same number, whether X equals Y. And they intend to communicate as much as is required to determine whether their private inputs, the numbers they're thinking of are the same, or alternatively, if the numbers that they're thinking of are different. They want to distinguish between those two cases. It's going to be cooperative. Okay, so there's no incentives at the moment. So Alice and Bob are just going to agree on a way of communicating. So communicating is just going to mean one of the parties sends a bit meaning a 0 or a 1, to the other party. Okay, and they do this repeatedly until they figure out whether or not X equals Y. Okay, so this is the cartoon picture you should have in mind about what happens in a communication problem. Okay. So more generally, what's the setup? So there's some function which is defined jointly on Bob's input, which is an n-bit string, so zeros and ones of length n, and an n-bit string held by Bob, and it's a binary function. So it's either going to be 0 or 1. Equality would be one particular example. And so Alice and Bob, again, it's cooperative. They can communicate up front, and when they communicate up front, they know the function f that they want to evaluate, like they know they want to compute equality, but at the time they settle on a communication protocol, they do not know their own functions. They do not know their own inputs, x and y. Okay, so in advance, Alice and Bob will figure out the most efficient way that they can communicate once they have x and y to answer this question, to figure out whether f is 0 or 1. So a little more formally, a communication protocol is just specifies rules so that at every step, it's unambiguous which of the two players is sending a message and what message that player should be sending. Now, for this to be well defined, anytime Alice or Bob sends a bit to the other party, this bit can depend only on what that player knows at that time. What does a player know? They know their own input, their private input. They do not know the other input. They also know what happened so far in their conversation. Okay, so the transcript of all of the messages sent so far. So as a function only of players' private inputs and the shared transcript of the conversation, it should be clear who speaks next and what is the bit that they send. All right? And we say that the protocol solves the problem, is correct, if when it concludes, and again it should be unambiguous when it concludes, one of the players, doesn't matter which, knows whether f of x comma y is 0 or 1. Okay? So that's the communication protocol. And we're interested in how many bits have to be sent in order to achieve this condition, in order for one of the players to know the answer to the question. So to measure that, for a fixed protocol, okay, so for a fixed way of transmitting bits, we say the cost of that protocol is just the largest number of bits that are ever sent. Okay? So this is going to be some function, usually of the input length n. Remember, Alice and Bob both have n-bit strings. One sec. So for a fixed protocol, we look at the largest number of bits that ever get sent, ranging over all possible inputs for Alice and Bob, x and y. And then what we're really interested in is not for a specific protocol, but for a specific function, for a specific computational problem like equality, what is the intrinsic communication necessary to evaluate the function? So in other words, among all correct protocols in the world, we want to look at the most efficient one, the one with the smallest cost. So the minimum cost of any communication protocol is defined as the complexity, the communication complexity of the function f. Yeah.
Might it also be reasonable to look at average number of bits that you need to send?
It is, and people do look at that. It turns out there is often not a huge difference. It turns out the average case is often not much better than the worst case in communication complexity. For something like NP hardness, the story is different. But often it's sort of convenient to work in the worst case world, but often the lower bounds that we generate are fairly robust. They suggest a distribution over which the problem would again be hard.
Like incompressible strings are actually very common. Incompressible strings of bits are actually very common, or?
Sure, but point being, or?
No, I mean, I guess that would generate the fact that the two would be roughly the same.
Okay. Oh, I see what you're saying. It depends. It's going to depend on the function f. It's not, I mean, so the distribution, which is hard for protocols, is going to be different for different f's. Yeah, yeah. Okay, good. So this is, this is one of the more technical slides in this part. Okay, so please ask questions if there are any. Okay, so again, communication complexity just says what is the, intrinsically, what's the minimum amount of communication necessary to evaluate a function, okay, by some communication protocol. So let's go back to examples. Let's go back to equality. So now we can talk about the communication complexity of the equality function, okay? So if you think about it, you realize, all right, well, the communication complexity is not going to be higher than n, okay, the length of the strings that Alice and Bob possess. That is, there exists a communication protocol that never sends more than n bits and always figures out whether they're equal or not. Is it clear what such a protocol might be? I guess I wrote it on the slide, actually. Right. So Alice, for example, could just send her n bits in order to Bob, and at that point, Bob knows whether they're equal or not. Okay? And that's always going to work. All right? So the question is, could it be smaller than n? Okay? Either it's equal to n or it's smaller than n. Is there a better communication protocol than this trivial one? And it feels like the answer should be no, I think. I think this would be most people's intuition. Right? So like, look at this. Suppose Alice had this input and Bob had this input. And think about the protocol we just did, where Alice sends her whole input to Bob digit by digit. So when Alice has sent her first 4 digits, they all match Bob's first 4 digits. But Bob does not at this point know whether or not they're the same string or not. Okay? Bob needs to know the 5th digit to figure out which case they're in. Now Alice could send the digits in a different order, but then again, maybe they all match except for that last digit. Okay? And Bob still doesn't know until the last digit. But I want to emphasize, this is not a proof. Okay? This is really not a proof that the communication complexity is at least n. The reason it's not a proof is that communication protocols can be fiendishly clever. Okay? They can do things that are very non-obvious. So who says that the protocol has to have Alice or Bob sending one of their bits to the other one? For example, Alice could instead sum up all of her digits and take them mod 2. So send the parity of her input to Bob. Not obvious why that would be helpful, but in some sense this communicates a little bit of information simultaneously about all of Alice's digits. Conceivably could be more useful. So there's sort of 2 takeaways from this. Sometimes the communication complexity of a problem is smaller than your intuition would suggest. There actually is a very clever protocol. Other times, your intuition is correct that you can't be the trivial protocol, but mathematically it's a challenging task to actually prove it, because you have to rule out not just that any obvious protocol works, but also over this very rich space of clever protocols, nothing works. Just to give you maybe a little bit of appreciation for non-trivial protocols, we're not going to talk at all about randomized protocols in today's talk, other than right now, because they're not important for us. But if you allow Alice and Bob to randomize, okay, so send message randomly, And you're happy that they evaluate the function f with 99% probability. Okay, so they have a 1% chance that they get it wrong, but 99% of the time they're going to be correct. Okay, where the randomness here is only over the coin flips of Alice and Bob. Okay, so for every single input, they're correct 99% of the time. Then, if you're allowed to randomize, you do not need to send n bits between Alice and Bob. You only need to send a number of bits corresponding to the logarithm of n, which is much, much, much smaller. Okay, so if n is like 1,000,000, they only need to send like 20 or maybe 40 bits. Okay, with 99% probability, they're going to know whether or not they're equal. Okay, the protocol, as just in case you're curious, the protocol is they just choose. They basically take a random inner product. So remember, we said a clever protocol could be take the parity of your input and send that. So instead, they take a random inner product of their input and send that to the other player. And the point is, if their strings are equal, random inner products will be equal. If their strings are different, random inner products will be different with 50% probability. You do it a few times, and if it passes all the tests, you're confident that you're 99% confident that actually the strings are equal. Again, none of that's important to remember or understand. This is all just to drive home the point that protocols can be non-trivial and interesting, and therefore that makes the impossibility result task even more difficult. Yeah.
But in this example, you implicitly assume that they share the same source of randomness.
So in fact, if they share the same source of randomness, the communication complexity is constant. So if they are allowed to flip their own coins, the communication complexity goes up to log n. So there's a non-trivial argument known as Newman's theorem that says actually any so-called public randomness protocol can be converted to a private coin protocol with an additional logarithmic number of bits. So I can tell you about that offline. It's sort of it's a Q proof, but it's not obvious. So it's even. So the logarithmic communication complexity is even when they have their own coin flips. I agree. The way I described the protocol sounded like a shared randomness protocol. Okay, but it can be extended. Okay. All right. So where are we? So just to recap, the communication complexity of equality without randomization, we know it's no more than n. We actually still don't know whether there could be a better protocol or not. And we'll prove a stronger statement than that, which will show that actually this intuition is indeed correct. Okay. All right, so questions so far? Yeah.
Is someone allowed not to send a message?
It turns out to not really matter. Yeah. So I mean, there's a lot of different tweaks of how you define communication protocols exactly, and they're all roughly equivalent. So you could ask, okay, does it, what if, there's a lot of, let's just leave it at that. There's a lot of variance, and it doesn't really matter for anything we're going to say today. Yeah. Other questions? Okay. So what's actually going to be, it turns out, crucial for proving impossibility results about auctions is an even more obscure variant of this model, known as non-deterministic communication complexity. Okay, which I want to say up front, this is going to be just a complete technical artifact. So the model I'm about to show you will not correspond to anything in the real world, but it turns out to be exactly the right tool for making statements about equilibrium of auctions. It turns out, as I'll show you. All right, so the way to think about this model is to think not about the amount of communication necessary for two parties to evaluate a function, but rather the amount of communication that an omniscient third party would require to convince Alice and Bob of some fact. Okay? So let's again think about equality. Okay, Alice has X, Bob has Y. But now suppose there's a third party who knows X and Y, and so therefore knows whether or not they're equal or they're not equal. And this third party wants to convince Alice and Bob of whatever the right answer is. Okay? So suppose X is not equal to Y. How hard is it to convince Alice and Bob that X is not the same as Y? Send them the
number of b to when they're different.
Good. So if X and Y are different, there is some bit in which they differ. So to convince them, I'll just say, hey, Alice, Bob, Alice, you have a 0 in digit number 17. Bob, you have a 1 in digit number 17. Okay? And Alice will say, yeah, you're right. I do have a 0. And Bob will say, yeah, I do have a 1. And at that point, Alice and Bob agree that clearly their strings are different. Okay? So this requires only, again, log an n number of bits to do the convincing. Okay, you need log n bits to encode which index you're talking about. All right? So convincing Alice and Bob that the strings are not equal seems to be much easier than them figuring out by themselves, which is not surprising. It seems like this omniscient prover, omniscient third party should be helpful. But what if you wanted to convince Alice and Bob that the strings are equal? You see any shortcut for how you do that? Yeah?
Send some large function of the string.
Send some large function of the string. And
Send some hash function in the string on the string.
okay, so we're not going to allow randomness. So we want to insist on correctness for every possible joint input. So if you allow sort of a probability of error, then I agree that's a solution, and that's a reasonable thing, especially if you're thinking about like the physical world. That's a very reasonable thing. But if we really want for every possible x and y there never to be a mistake, then it's not obvious how an omniscient prover, even though it knows x equals y, how would you unequivocally convince Alice and Bob of that fact? Okay? So that Alice and Bob are 100% sure that the strings are equal. Okay? Not obvious. And in fact, as we'll see, and I'll prove to you, there is no shortcut for an omniscient third party to convince Alice and Bob that x equals y. Okay? Alice and Bob may as well just run the trivial protocol with Alice sending her whole string to x. Okay? All right, so that's going to be the last thing we do in the sort of just pure communication complexity part of the talk. I want to actually prove to you that for equality, convincing Alice and Bob that x equals y, you really need n bits just to do the convincing. Okay? Now I'm going to prove this statement not because we actually need this statement. Okay? In the next segment, we'll move on to problems we actually care about, welfare maximization. But I want to give you a little bit of a flavor for how these impossibility results work, mostly because I don't want you to be frightened of them. Right? So if you want to dig deeper, okay, I hope you'll be convinced from this part of the talk that this is something you just totally understand quite quickly. This is not trying to pick up algebraic geometry over the weekend or something. Okay? So that's why I'm doing this proof, to give you a flavor of the types of techniques. They're basically sort of glorified counting arguments in a way. There was a question, yeah. So I will, for example, write down the index of the bit in which x is not equal to y, and maybe I also say, you know, who has the 0 and who has the 1. I just write it down in binary. So if it's index number 17, I'll just write the number 17 in binary. Yeah. Other questions? All right, so let me prove to you that actually the complexity of convincing Alice and Bob that x equals y is as big as it could be, is in fact linear in the length. So to do that, I need to be, yeah.
Trivial question.
Yeah.
Why is this called non-deterministic if there's no randomness?
So in computer science, there's a distinction between non-determinism and randomization. So they do not mean the same thing. So for example, if you've ever heard of the term NP-complete or NP-hard, okay, so number one rookie mistake about NP hardness is to think that NP stands for not polynomial. Okay? That's not, it does not. Okay, never think that. Honestly, my advice is try to forget what NP actually stands for. It actually stands for non-deterministic polynomial, it turns out. So non-deterministic really refers to kind of, I think of it as this way, complexity of convincing someone. So if you like certificate complexity. Okay, so same thing with, like, say, the traveling salesman problem. It's easy to convince you that there's a short one. I just write it down. Not so easy how I would convince you that there isn't a short one. So it's the same kind of sort of proof complexity, if you like.
I was just wondering why this word.
So right, so
What is determinism?
okay, right. So
Not deterministic.
that's okay. So there's an equivalent version, the classical version of this model. You don't describe with a prover. You describe where Alice and Bob non-deterministically guess what bit to send next, and then you define correctness as being there exists an execution path so that they correctly evaluate the function f. But there's an immediate isomorphism with this version of the model, where the prover just writes down that execution of their guesses where they would evaluate the function. Yeah. Good question. Okay. So to prove the lower bound, I need to be a little more precise about the model, but I think you can already guess what it looks like. So Alice and Bob still have their private inputs. An omniscient party knows x, y, and writes something down. Okay, so the prover writes down an alleged proof. Think of it as on like a publicly viewable billboard. Okay, so both Alice and Bob can regard this alleged proof. And the prover also says which, whether the proof is supposed to prove that f equals 1 or f equals 0. And Alice and Bob, in this version of the model, they don't even need to communicate. Alice will just look at the alleged proof and look at her private input x and decide whether or not she accepts the proof. Bob does exactly the same thing in parallel, obviously referring to his private input y, independent of x. So for example, in our equality protocol, the prover would write down the index of the bit and also would specify which of the two players has the 0. Alice could then check that that was legitimate, that if she supposedly has a 0 in 17, then she could say, yes, that's true. Bob could check that he does indeed have a 1 in digit number 17. Okay? And so what does correctness mean? So correctness means that the prover should never be able to convince Alice and Bob of something that's false. So if the strings are equal, Alice and Bob should reject any alleged proof claiming that they're different, and vice versa. That's what correctness means. So the cost of the protocol, well, the only communication is what the third party writes on the billboard, so the length of the proof and the number of bits. So that's the cost of the non-deterministic protocol, and again, the communication complexity is just the shortest worst case proof length, okay? Short minimum protocol cost. So any questions about this? Yeah. Yes. Yeah, they know F in advance. So Alice and Bob sort of coordinate on what they're going to do, knowing F, but not knowing X or Y. Yeah. Yeah.
We're confused about the definition of correctness, so do we also require that they do indeed accept it when F works?
I guess so, yes. Yes. Otherwise, they could always reject. So I apologize. Yeah, this is actually underspecified. It should also be the case that there exists something the prover could write down so that, but in some sense, I guess that part's sort of trivial. I mean, the prover could sort of, yeah, as you say, right. So it should always be the case that there exists a proof that convinces Alice and Bob of whatever F is. Thank you. Good point. Okay. So let's put all these together. And again, the point of this is just going to be to show you the types of arguments that are used to prove these kinds of impossibility results. So the claim is that the non-deterministic communication complexity, so the cost of convincing Alice and Bob that strings are equal, is in fact matches the trivial upper bound of n. Okay. Let me point out that any lower bound for the non-deterministic model certainly holds also for the deterministic model. If you have a good deterministic communication protocol, one option for the prover is always just to write down what the transcript would be in that deterministic protocol. And Alice and Bob can say, yes, that is in fact how I would act in that protocol. Okay? So lower bounds for the non-deterministic case are only stronger statement. All right, so let me show you the proof. The proof is not hard. Okay? It's slick, not hard. So here's a lemma, very important lemma, okay, in communication complexity. So fix a proof that the prover might write down. Okay? Say a proof that the two strings are equal. Okay? Suppose Alice and Bob both accept this proof when Alice has x1 and Bob has y1. Suppose Alice and Bob also accept this exact same proof, pi, when Alice has x2 and Bob has y2. Okay? Then I can actually show you two further inputs where Alice and Bob will both accept this proof pi, namely the two mixed inputs, x1 comma y2 and x2 comma y1. See that that's true? So this is true because Alice and Bob accept or reject based only on what they know, which is their own private input and the proof that's on the blackboard, pi. Okay? So if Alice has private input x1 and sees the proof pi, for all she knows, Bob has the input y1. Okay? Which means she's going to accept. And then the same argument in reverse. Okay? And so that means they're also going to accept on these two mixed inputs. Okay? So that's the first lemma. And this actually drives an enormous, this is sort of actually the sort of most basic building block of a lot of lower bounds in communication complexity. Which part? Why is it true?
Yes.
Yeah, so suppose suppose the prover writes pi and Alice happens to have the input x1. For all Alice knows, Bob has the input y1. So she's going to accept. Okay? Alice will accept the proof. Okay, so this says whenever pi is on the blackboard and Alice has x1, she will accept. Yeah. And over here we see that whenever Bob has y2 and pi is on the blackboard, Bob will accept. And so that means x1, y2 will be accepted by both. Yeah. Other questions? It's sort of deceptively simple. It's actually a really important lemma. Okay, so how do we use this to get our lower bound on equality? So here's now something which seems sort of interesting, which is I claim the prover cannot reuse any proof. So if you take any two different strings, W and Z, the prover must use a different proof to convince on the input W comma W to convince Alice and Bob that the strings are the same. A different proof than it uses when the input is Z comma Z to convince Alice and Bob that the strings are equal. Okay? So for every string, the prover must use a different proof to convince the players that the strings are the same. Okay? This follows immediately from the lemma. If the prover tried to use the same proof for the inputs W comma W and Z comma Z, then not only would Alice and Bob accept the proof in those two cases, they would also accept it when one of them has W and one of them has Z. Okay? But that violates correctness. And the prover should never be able to convince Alice and Bob of something that's false. Okay? And they're allegedly convinced that they're equal when in fact they are not. Okay? So each input of the form W comma W needs its own proof. How many inputs of that form are there? Well, there's 2 to the n different choices for what the string could be. So the prover, ranging over all inputs x and y, the prover must make use of at least 2 to the n distinct proofs. The number of distinct proofs with length less than n, right, is at most 2 to the n minus 1. So some of those proofs must have length n. And so that shows that the non-deterministic communication complexity is at least n. Okay? So any questions about that? Yeah.
Where you use the assumption that it's non-deterministic?
Well, what do you mean? So for the lower bound, it's an only stronger statement that it's not deterministic.
To have repeated this proof word by word in case of deterministic case.
I agree, but this is a stronger statement. So I need the stronger statement for the later applications. Right, so it's a stronger statement to have a lower bound for the non-deterministic case than it is for the deterministic case. So I'm proving the stronger statement here. Which again, I need. I'm not doing it just for math's sake. I actually need this. Okay, so this is all the pure communication complexity I wanted to tell you about. So,
What is this fooling set that we're doing?
oh, that's just the name of the inputs of this form. Yeah. So it's a bunch of inputs where, you know, it's exactly what, so it's a bunch of inputs that force you to use a different proof for each one because of this lemma. That's the name of it. Okay. So right now you should be like, okay, hopefully you followed everything. If you didn't follow everything, ask me. It should maybe seem weird and arbitrary and unrelated to everything else. That would be the normal headspace to be in at this moment. Okay? All right, so let me now get this a little closer to what we care about, auctions. So I'm going to still talk about communication complexity, but at least I'm going to talk about not toy problems like equality, but actually the problems that we've been caring about in these lectures, namely welfare maximization in markets. So now I'm going to talk about lower bounds on communication complexity for welfare maximization problems. So here I'm not going to do the proofs, I'm just going to give you the statements, but the proofs are, you know, slightly more complicated versions of, you know, what I just showed you. I've done all of these proofs self-contained in a graduate class, and there's lecture notes if you're interested. So, you know, don't feel like that this is inaccessible to you. All right, so if we care about welfare maximization, you know, what might be a problem that we care about? So we're actually going to prove lower bounds for a simpler problem than welfare maximization. Okay, so it's only going to be a stronger result, lower bound for an easier problem. I'm just going to assume we want to differentiate between the case where there is a high welfare allocation and the case where all allocations have pretty low welfare. Okay, that's going to be the function I'm interested in evaluating. So thinking ahead to auctions, we're now not just going to have Alice and Bob. We're going to have n different parties corresponding to the bidders in one of these auctions. The private input, so now it's not going to be an n-bit string, it's going to be just a valuation. Okay? That's the private input of each of the players. And what the players want to understand, they want to evaluate a function f defined on all of their private inputs. And they want to figure out whether or not there's an allocation that has welfare at least w, maybe w is like 1,000, or whether every allocation has really small welfare. Let's say we take alpha to be like 1%, and then this would be, you know, 10. All right? So that's what the players need to figure out. Is it possible to achieve social welfare at least 1,000, or is it impossible to do better than 10? And to make the problem even easier, making our lower bounds even stronger, in the middle, you're off the hook. I'm not going to actually insist that a protocol do anything sensible if the maximum possible welfare is between 11 and 999. All I insist is that the protocol is correct on the extremes, where there's a really good allocation or all allocations are really bad. Okay? That's going to be the problem I'm interested in. Okay. This is what I just said. So correctness is modified so that we only care about being correct when f in fact is 1 or 0. F is undefined if neither of these two things hold. Yes, it is. Sorry. That should be strictly greater than alpha W. Yeah. Thank you. Yeah. Yeah, I think I meant to write here every allocation has welfare at most alpha W, but I mixed it up. Thank you. Okay. So this is a function. We can talk about the communication complexity of this problem. Okay, we can talk about the deterministic version, but again, for the auction applications, we need to talk about the non-deterministic versions. Yeah.
Aren't the V's like potentially real numbers? So that
Good question. Yeah. I was hoping in a crowd of economists nobody would ask me about encoding issues, but okay, fair enough. So to make the problem still even easier, let's assume that everybody's value for every set is always an integer between 0 and some not very big number. So it turns out the lower bounds will even be true then. Okay? But you're right. So, what is VI really? It's a list of 2 to the m numbers, where each number is encoded in some modest number of bits. Okay? So that's one thing so what used to be n used to be the input length. Now n is the number of players, and the input length is actually more like 2 to the m. Because again, this valuation specifies 2 to the m different numbers. Okay? So there's a little notation switch. All right, so I want to talk about the non-deterministic communication complexity of problems like this. In other words, the cost of convincing you that we're in one of these two cases. Now, just like with equality, where one of the cases was easy to convince Alice and Bob, and the other case was hard, we're going to have the same thing here. So which is easy to convince the parties of? F equals 1 or F equals 0? F equals 1. Okay? It is not difficult to convince, for an all-powerful prover, to convince the players that there is a high welfare allocation if one exists. Because if one exists, the prover can just write down that allocation on the blackboard. Okay? Just specify who gets which items, and maybe specify everybody's values for the bundles that they get. Everybody can look up there and say, yes, that is indeed my value for that subset, and I do see that that's a high welfare allocation. Okay? So when we talk about difficulty of convincing the players, this is going to be what's difficult. How would you convince somebody that all allocations are bad? I could show you some bad allocations, but what about all the ones I'm not showing you? Okay? So this is where the lower bound is going to be. Okay, so the non-deterministic model, it's what you'd think compared to before. So again, the prover is going to write down an alleged proof, also specifying whether they're trying to prove the high welfare case or the low welfare case. All players simultaneously decide whether or not to accept or reject. And correctness means that that there should always exist a proof that convinces the players. Again, I forgot to write that down. And also that the prover can never convince the players of something which is false. And again, if it's one of these sort of intermediate inputs where the optimal allocation is neither high nor low, the protocol's off the hook. We just declare it to be correct no matter what it does. Okay? All right. Yeah.
Why is any communication necessary here? Players are smart. They know how to solve mechanism design problems. They can work it out themselves without any communication.
How would they do that?
Sorry?
How would they do that?
How would they do that?
I mean,
Smart. They know mechanism design. They don't need any communication.
but they don't know each other's valuations, right? So I'm in no position to have an opinion about the optimal allocation if I don't know what your values are. Right? So say there's even 2 of us and I'm trying to split m items between us. Which part should I get? Which part should you get? I can't speak about that without knowing something about your values.
Every player knows only his own valuation.
Correct, yeah. And that's crucial, obviously. Yeah. So that's what I mean by private inputs. I mean, player I knows VI and knows absolutely nothing about the VJs for j not equal to I. So that's why they need to communicate. Okay, good. So, yes, convincing you that there's a high welfare allocation is easy. Convincing the players that there's a low welfare allocation is hard. This is just like how we prove that with equality, convincing two players that the strings are equal is hard. It takes long proofs. Okay? So let me give you the fairly precise statements. There's going to be two statements. So first, let's assume we make no assumptions at all about the valuations. Okay, non-negative and monotone, if you like, but nothing else. In particular, for this first statement, we allow strong complementarities between items. Okay, so we want a protocol that works for all possible valuations. So for every constant, alpha, bigger than 0, as small as you want, okay, 0.01, 0.001, whatever. For alpha as small as you want, if I take the number of items m large enough, it is the case that every non-deterministic protocol that differentiates between the case where there's a high welfare allocation and every allocation is an alpha fraction worse than what you're shooting for has extremely large proof length, okay, namely exponential in the number of items m. Okay? So, and remember, that's the trivial kind of lower bound. Okay, so remember, if nothing else, the prover could just write down everybody's valuations on the blackboard. That would have length, 2 to the m times some factors. Okay? So what this is saying is there's basically, no way much better of convincing the players that all allocations are bad other than just sort of telling everybody's valuations. Okay? There's a question? Okay. Okay.
So that's true also for n equals 2, say?
No, it's not. So you need n to grow large as well. Yeah, n needs to grow like the square root of m, I believe. Yeah, because you can get alpha equal 1 over n. So there is a good protocol if you only care about a 1 over n gap. So for alpha to go to 0, n must grow large. Yeah. Okay. So that's the first statement. And again, I'm not going to prove it, but it's again these sort of, you have a lemma which says that, the proofs, the common, you can't reuse a common proof for lots of different inputs. Okay, that's again the flavor of where this comes from. All right, so this is for the general case. So this says, even just certifying the welfare maximization problem is hard for general valuations. What if we impose some structure on the valuations, like we were doing yesterday? Okay. So let me talk about subadditive valuations. The definition actually appears on a later slide, but a subadditive valuation is just like what it sounds like. Your value for the union of two bundles is at most the sum of your values for each of the bundles. Okay, that's what subadditive means. I'll explain this later, but that's a weaker assumption than submodularity. Okay, so this is certainly a restriction compared to the general case, but it's actually a relaxation of the submodular case we were talking about yesterday. So here it's no longer true that you can have a lower bound for arbitrary constants alpha, but for every constant bigger than 1/2, if I take m large enough, differentiating between the high and low welfare cases again requires proof length exponential in m. Okay? So in particular, figuring out what the maximum possible welfare is up to a factor bigger than 2 is a difficult problem. It requires exponential in m communication. Okay? Yeah.
Thinking about applications like spectrum options, whatever.
Yep.
Of what use are the results when m is very large? So we are saying like 100 bundles, like 100 items, right? Here maybe this exponent kicks in when m is like 10,000.
Yeah, so one thing that's cool about communication complexity, which again is sort of different than computational complexity like NP hardness, is here you actually get explicit bounds on exactly how much communication is required as a function of your parameters, even for very small m and n. So these lower bounds are going to be meaningful. I mean, people haven't really worked hard to optimize the constant factors inside these lower bounds, but you will get meaningful lower bounds here even for values of m that are in the range of what you see in spectrum auctions. So, I write exponential here, but there's some specific formula here. 2 to the m over 4 times n squared or something like that. And so if you plug in practical values of n and m, it's actually going to be an extremely big number. Now, a different comment which you could make about complaining about salience to real-world auctions is, this is, as with all of these negative results, it's a worst case result. So I'm just saying, there are valuation profiles where you'll use a lot of communication. And as always, in the face of impossibility results, you should try to think about additional assumptions on inputs so that you can get better positive results. And this is in the subadditivity restrictions in that same spirit.
I must have misheard something. I thought when you introduced subadditive just now, you said that would make things easier, but the result seems to be the same.
No, so this is so here it's arbitrarily small alpha.
It's the
Exactly.
difference of analysis.
Exactly. So you're right that the lower bound and the proof length is the same,
Yeah.
but the factors involved are different.
Okay.
Exactly. And so I should say, looking ahead, these alphas are going to correspond exactly to negative results for the price of anarchy. So like our 63% from yesterday, that's going to be one of our values of alpha that we think about. Yeah.
So exponential in M, I should understand that basically all the values have to become known.
All the
Values, or all the
that's
values,
right. That's right.
basically.
Qualitatively, yeah, exactly. So just like with equality, there's no easier way to convince you that the strings are equal is just writing down one of the player's inputs. Here, it's not quite as tight. I mean, it's not literally the same number like it is in equality n, but roughly it says you basically may as well write down everybody's valuations on the public blackboard and let people discover for themselves then which case you're in. I think it's exponential in m over n squared. That's my recollection. No, so alpha will never be, you can always get a 1 over n here. So you need n to be going to infinity, but slower than root n is what you need. Yeah.
Subadditivity essentially means substitutability. But you said that the complementarity case is the hard one.
Right. Right. So complementarities are allowed only in this version of the theorem. Right. So here we have no restrictions on the valuation, so there can be complements. Here there is a restriction, subadditivity, and you could argue about to what extent subadditivity eliminates complements, but to some extent it does. So you should think of this as sort of a complement, a relatively weak complement-free condition, and then here we have it. And so that's why we're seeing a stronger, notice, I mean, this is a stronger negative result, right? This says even if I set alpha to be 0.0001, I still can't convince you which case we're in without basically writing down everybody's valuations. Here I'm not claiming that. I'm just claiming, for alpha equal 0.51, I can't convince you which one that we're in. And indeed, if alpha was less than 1/2, there is a protocol that, which does not use much communication that convinces the players which of these two cases you're in. Okay? So this is not just, as we'll see, this is not just an artifact of the proof. This is actually tight for subadditive valuations. Okay. So again, just to remind you where we are. Okay, so I gave you an intro to communication complexity, and those types of proofs prove these theorems. And these theorems, again, it's not clear why you should care about it. Non-deterministic protocols isn't really like a model that we care about. So I still have to connect these to equilibria. That's the rest of the lecture. But at least, and that should be plausible, that communication complexity has something to say about what auctions can do. Because it can at least say about what protocols can do for the underlying optimization problem. Okay. All right. So let's actually now, reap the benefits of this investment. Let's talk about optimal simple auctions. Okay. So we talked about positive results for simple auctions yesterday. I focused mostly on submodular valuations yesterday. I'm actually going to change the story a little bit, and you'll see why at the very end of the lecture. So I'm going to switch to subadditive valuations, which I mentioned on the last slide. So again, here's the definition of a subadditive valuation. Your value for the union of two bundles is at most that of your sum for each of the bundles separately. In terms of our sort of cartoon of different types of restrictions you can impose on valuations. So yesterday we talked a little bit about unit demand, where a player only wanted one of them. That was a special case of submodular, gross substitutes wedged in between. Subadditivity is a relaxation of submodularity. Okay, so it's only a harder problem to deal with bidders with subadditive valuations. So whatever price of anarchy bounds we saw yesterday, they can only conceivably get worse. Okay? And indeed, they actually do get a bit worse if we relax the hypothesis to subadditive valuations. What used to be 63% is now 50%. Okay? And as we'll see, this is tight for the subadditive case. Otherwise, this is exactly the same theorem that we ended with yesterday. Because the two differences are this weaker assumption about bidder preferences and this weaker bound on Bayes-Nash equilibria. It is, again, an arbitrary product prior distribution over subadditive valuations. Okay? So what I want to show you is how the work we've done so far actually implies, combining with this upper bound, implies that simultaneous first price auctions, the mechanism we were talking about yesterday, it's actually in a precise sense the best possible simple mechanism for achieving welfare guarantees with subadditive valuations. Okay, nothing has a better worst case guarantee. Okay, that's something we'll be able to derive today. Okay, so first let me just start with something more modest. So notice I'm citing two papers here. So Feldman, Fugravin, and Lussier, they proved the positive result. Okay, so they proved that every equilibrium is within 50%. That's very interesting. Also very interesting is a construction by Christodoulou et al. Showing that there are examples. Okay, so you can specify subadditive valuations for the bidders, and you can specify a Bayes-Nash equilibrium so that the welfare at that equilibrium is in fact 50% off from the best possible. Okay, so the analysis in Feldman et al. Is tight. So how did Christodoulou et al. Prove that? Well, they prove it probably the way you'd think that they'd prove it, which is by an explicit construction. Okay, so they literally just write down valuations for everybody. They solve, so they prove the lower bound even in the full information case. So they solve for a mixed Nash equilibria. And as most of you in this audience know, solving for a Nash equilibrium in a game with lots of players with lots of strategies is very difficult. Okay, so this construction is a tour de force. It's very difficult to prove this result. So they write down the valuations, they solve for the equilibrium, and they just compute the welfare at the equilibrium, and they know what the optimal is, and they just show that there's a factor 2 gap. Okay? And this is sort of, I would think, the obvious way, not necessarily easy, but the obvious approach to proving impossibility results for specific auction formats. Okay? Write down a bad example. Okay? So by building on the communication complexity toolbox I showed you, we're going to get two benefits compared to this approach with explicit constructions. First of all, we'll be able to generate these exact same kinds of negative results for specific auction formats, but without having to write down an example and solve for an equilibrium. So technically, we're going to be able to get these kinds of negative results, but in a much easier way, by standing on the shoulders of communication complexity. But there's a second thing which is even more important. Okay? So the negative result, the construction in Christodoulou et al., it is tailored to the specific mechanism. It is tailored to the fact that we're talking about simultaneous first price auctions. If you change the auction format just a little bit, say from first price to second price, or first price to all pay, or if you add some bells and whistles, as this audience knows, you change a game a little bit, it's very hard to figure out what happens at the equilibria. So you basically have to redo the exercise for each little tweak to the auction format. So with explicit constructions, I can't imagine any way you could have a negative result that applies to a wide swath of auctions, any reasonable notion of all simple auctions. Whereas the communication complexity toolbox will let us make statements of exactly that type. We will improve impossibility results not just for one auction format, but for every simple auction format, no matter how clever. Okay? All right. So, yeah.
What was the question?
Is there a simple intuition for the 50%? I mean, the best thing I can say is that the proof in the Feldman et al. Paper is based on sort of a symmetrization idea, which when you combine with the subadditivity assumption, it's sort of natural where the 50% falls out of that argument. So basically, if you have a subadditive valuation and you split the item set into a random 50% of it, the expected value of that is going to be half of the full bundle. That's about the best intuition that I have. I mean, in a sense, arguably, the strongest evidence for the 50% being fundamental is going to be this theorem. Okay, as we'll see. Okay, all right. So again, I was just talking about what if we vary the auction format? Okay, so these two papers gives us a tight analysis of simultaneous first price auctions, 50%. We might not be so happy with 50%, right? We had higher numbers yesterday. So can we do better? We can't do better with this auction format. There's no slack in the analysis. But can we have a smarter mechanism and beat 50%? Now, we don't want to resort to the VCG mechanism to get 100%. We want some auction where it's plausibly implementable and so simple in some sense with some kind of reduced message space. Okay? And we're going to see the answer is no. You cannot do better. Okay?
So,
Yeah.
not resulting to VCG. It said on the previous slide.
Yes.
What is the criteria? What exactly? This is
So-
VCG as an example.
So, I mean, this question as posed is not very interesting because the answer is just yes, without constraints on the design space.
Right. So what exactly is the constraint?
Yeah, so I have to, that I have to say. Just fast forwarding a little bit, it's basically going to be that the message space has sub-exponential dimension. Yeah. Okay. All right, so I'm going to skip this actually. Yeah. Okay. So this is going to be, the main theorem for the remainder of this lecture. The point of this theorem is to show that the communication complexity lower bounds that we've already established for welfare maximization problems translate in a black box fashion, so just in an automatic fashion, to impossibility results on the best possible price of anarchy, the best possible equilibrium welfare guarantee of any simple auction. Okay? So here's the hypothesis of the theorem. So we have some class of valuations that we care about. Maybe it's general valuations, maybe it's subadditive valuations, maybe it's modular valuations, whatever. But suppose if we look at the welfare maximization problem for this class of valuations, we've proven already that it's hard to differentiate, hard even non-deterministically, to differentiate between the case of high value, okay, where there's an allocation at least W, and low value, where every allocation is at most alpha W. And we know this is a meaningful hypothesis because we literally already examined statements of this form. Okay, so for general valuations, this is true for arbitrarily small alpha. For subadditive valuations, this is true for alpha arbitrarily close to 1/2. We already know that. Okay, so we have examples where the hypothesis is satisfied. So what's the conclusion? Right, so the conclusion is impossibility results for equilibria of simple auctions. Okay, so let me walk you through this. So again, think about the exact same valuation class we started with. Pick an arbitrary simple mechanism. What's a simple mechanism? Well, so formally, again, for a crowd of economists, the way I recommend thinking about this is that the number of dimensions of the bid space or of the message space is sub-exponential in M. Okay, so don't forget the dimension of the type space. Every bidder has a valuation profile with 2 to the M parameters. So any direct revelation mechanism would have 2 to the M dimensions in the bid space. The definition of a simple auction here is that you have significantly less than 2 to the M dimensions, sub-exponential. Okay? 2 to the root M, M to the 10th, M squared, whatever. Again, just to sort of calibrate you, let's go back to simultaneous first price auctions. Okay? They better qualify as a simple mechanism, okay, for any of this to make sense. So what's the dimension of the bid space in simultaneous first price auctions? It's linear in M. It's just M. Each bidder submits 1 bid for each of the items. Okay? So here it's a much more permissive definition. Okay? Certainly dimension M qualifies as simple, but even dimension M squared, M to the 10th, 2 to the root M, etc. Okay? All of those are allowed. But no matter how many dimensions you use, unless you go all the way out to exponential, what the theorem asserts is that there will be valuation profiles from the class you're talking about, and there will be equilibria, so that the welfare of that equilibrium is no more than an alpha fraction of the maximum possible. Okay? So the worst case price of anarchy, worst case overvaluation profiles and over equilibria, the worst case price of anarchy of any simple auction is at most whatever, at most the same alpha, same factor alpha, which appears in the communication complexity lower bound. Yeah. Right. So this is written so that it's, this is written in sort of more computer sciencey language. So here's one way to think about it. So suppose you have a bid space with d dimensions. Okay. How many different actions do you have available to you? Well, it's going to be exponential in D. Okay, so so what's confusing is, so for the communication complexity model, it's important we work with bits. Whereas often in the mechanism design literature, you think in terms of real numbers. So you have to translate between the two. But basically, the number of actions is exponential in the number of dimensions. So if you think about like a direct revelation, so maybe here's a good way to put it. Think about a direct revelation mechanism like the VCG mechanism, and assume that my value for every bundle is like either 0, 1, or 2. Okay, so it's a very trivial subset of general valuations. Then, how many actions, what's my action space? Well, for each of my 2 to the m parameters, I have 3 different choices. So it's like 3 to the 2 to the m different actions. And that's even if I discretize to a small number of possible valuations. Okay? So in the direct revelation case, the bidding dimension is exponential. The action space size is really doubly exponential in the number of items n. And so the technical requirement here, again, because it's based on communication complexity, is just suppose the action set is sub-doubly exponential. Okay? And in particular, for any kind of message space type setup, that would require a sub-exponential dimension. Yeah, good question. All right. So one piece of sort of annoying fine print is that actually what I just said isn't quite right. The lower bound applies for the worst epsilon approximate equilibrium, okay? Where epsilon can be very small. It's not 0. I actually do not know if this theorem is true with epsilon equals 0. I'm curious, but I don't think conceptually it's that important. But it is true for epsilon even going to 0 very quickly with the number of bidders n and the number of items m. Now remember, okay, when we talk about the price of anarchy, we're talking about the worst equilibrium. So when you pass from exact equilibria to epsilon approximate equilibria, there's only more of them, so the price of anarchy can only be worse. So that makes this lower bound weaker than it would be if epsilon was equal to 0. Okay? So that's just sort of some technical fine print. All right? Okay, so any questions about the generic theorem? Otherwise, I'll put the pieces together and we can actually, we're now ready to actually state some formal, optimal, simple mechanism theorems. Yeah.
Where alpha comes from? So it's for every alpha, or it's one half that we have before?
Good. So alpha is in the hypothesis, and so the alphas for which the hypothesis is true will depend on which class of valuations you're talking about. So if we take V to be all valuations, the hypothesis is true for every alpha bigger than 0. And so we get the conclusion for every alpha bigger than 0. If V is instead the class of subadditive valuations, we get the hypothesis for every alpha bigger than a half. And so we get the conclusion for every alpha bigger than a half. Yeah. Okay.
Are
Yeah.
you talking about relative or absolute epsilon approximate mesh?
Let's see. I don't think it matters because, basically because it can be so small. Yeah. The way it's stated in the paper, it's additive. Yeah. Yeah. Okay. So what? Well, now let's put the pieces together. Let's put together the communication lower bounds we've already stated with that main theorem. So let's start with the case of subadditive valuations. So this is exactly the same theorem I showed you earlier. So for all alpha bigger than a half, even non-deterministically, it's difficult to differentiate between high and low welfare for alpha bigger than a half. So if we apply the main theorem, we get black box, okay, just immediately, that for every auction where the bid space is sub-exponential in the number of items, the worst case price of anarchy, again, worst case over valuations that are subadditive and over equilibria with respect to that valuation profile is going to be no better than 50%. Okay? So as a result, right, remember we had this positive result for simultaneous first price auctions that the price of anarchy actually is 50%. So in this sense, simultaneous first price auctions are an optimal, simple mechanism when bidders have subadditive valuations. Okay? So this is a sense in which you can actually define simple mechanisms and prove optimality results for them. Let's talk about the general valuation case. This again is exactly the same theorem I stated a few slides ago, saying that for every positive alpha, if valuations are general, there are strong complementarities. You can't differentiate between the very high and very low welfare cases. So again, applying the main theorem as a black box, every simple mechanism, so there is no simple mechanism that can guarantee 1% of the optimal welfare at equilibrium. There is no simple mechanism that can guarantee 0.1% of the maximum welfare at equilibrium. All of these are impossible. Okay, and this follows from the communication complexity lower bounds. So how to interpret this? So one way to interpret this, so that in the economics literature, a lot of blood and ink has been spilled over the question of, whether you should augment simultaneous ascending auctions by, very complex, extra instruments like package bidding. And if you like, you can interpret this corollary as supporting the argument. The complexity should be added to, say, spectrum auctions when you think the complementarities and the preferences are dominant. Okay? This is a formal sense in which you really need complexity, like package bidding, in order to get any kind of welfare guarantee. Okay? And let me point out, right, so let's not recall where we started with trying to translate these folklore beliefs into rigorous statements. We look at this corollary, right? So no simple mechanism has a non-trivial welfare guarantee for bidders with general valuations. That actually does seem to map on pretty closely to that second folklore belief. So with strong complements, for us that meant with general valuations, no restrictions on the valuations. Simple auctions aren't good enough. So we define what this means, sub-exponential bidding dimension, and we define what not good enough means. It means there's literally no constant factor approximation. Okay. So questions?
How do you prove it?
How do you prove it? Yeah. Right. So I'll tell you a little bit about why it's true. Okay. Just in case you're curious. Okay? If you're not curious, feel free to tune out for the rest. Okay. Proof's actually not very hard. It's like a lot of stuff in complexity theory. It feels like a strange argument, but it's not a long argument. Okay. All right. So both to kind of tell you about a tool I'm going to need in the proof, and also to explain where this annoying epsilon comes from in the theorem. Let me talk a little bit about the description length. Okay, so if you have to write down a Nash equilibrium of a game, how long does it take you? Okay. Think about simultaneous first price auctions. And again, let's assume that we're insisting that valuations are integers in some reasonable range, between 0 and some maximum integer, V max. Okay? Now, how many strategies does each player have? Well, as we mentioned, it's singly exponential in the number of items n. Okay, so this many options for each of the, let's see. Oh, sorry, we're not talking about, right. So in the bid space, right, so you have to submit a bid on each of the m items, and these are the number of different bids you can submit on that item. Okay, so this is the size of your action space. Okay. Now, suppose I wanted to write, so let's even just think about the full information case. Suppose I wanted to write down a description of a mixed strategy, Nash equilibrium, of simultaneous first price auctions. Right, so to write down a mixed strategy even of a single player, okay, to write down a mixed strategy just of one player would require me to write down potentially one number for each of its actions. Okay? So the description length of a mixed strategy is exponential in m. So what? Why do we care? Remember, all of our lower bounds are for things that are sub-exponential in m. Okay, so this will cause a problem in the proof, the fact that it takes so many bits just to write down a Nash equilibrium. Okay? Trust me for the moment that that would be a problem in the proof I'm going to show you. So, what's the fix? So for the fix, we're going to use the fact that every game, okay, so in general, when you have a game, like rock, paper, scissors, and generalizations, Nash equilibria have full support. Right? Players randomize over all their strategies. Okay? And you're stuck with that with exact Nash equilibria. But here's a really useful fact. If you're willing to accept epsilon approximate Nash equilibria, then in fact, there's always such an equilibrium with extremely small support, where each player randomizes over very few of its available strategies. Okay? What do I mean by very few? Well, let's think about a game with n players. Okay? Capital N strategies per player. Okay, so for exact, you might need a supportive size n. So for any game, okay, no assumptions, there's an epsilon approximate, mixed Nash equilibrium, meaning everybody's best responding up to plus epsilon. where the support size, meaning the number of strategies that each player randomizes over, is polynomial in n, 1 over epsilon, and here's the important part, the logarithm of the number of actions. So again, for an exact Nash equilibrium, you might have to randomize over everything, all n of your strategies. If you're willing to tolerate an epsilon, you can randomize over far fewer, log of capital N instead of n, okay, which again is much, much smaller number. Okay? The proof of this is actually not very difficult at all. Basically, you just say start from an exact Nash equilibrium, you know one exists, and now sample pure profiles, pure strategy profiles, independently and repeatedly from this mixed Nash equilibrium. Do that this many times, and then just look at the empirical distribution. Okay? Each player just says, oh, how frequently did I play each of my actions in the sampled profiles? I'm going to use the empirical distribution over the samples as my mixed strategy. Okay? And by concentration of measure type arguments, because you started with an exact Nash equilibrium and you took enough samples, everybody's going to be best responding up to an epsilon. Okay? So this is an important theorem, but it's not particularly hard to prove. No, so each player independent, so you don't do the empirical distribution of the profiles. Each player separately says, how frequently did I play each item? And then again, you use the product of those marginals. Yeah. Okay, and so now to tie this back in, so that means in simultaneous first price auctions, where capital M is only singly exponential in M, it means there's an epsilon approximate Nash equilibrium that you can describe very succinctly. Okay? There's one in which each player is randomizing only over linear in M number of actions. Okay? And that's going to be important for us in the proof. Okay? So for every game, so for example, for these simple auctions, I can write down an approximate Nash equilibrium with very small description length. Description length essentially logarithmic in the number of actions, in the action space. Okay? All right. So this was the theorem. So let's actually talk about the proof. Proof actually fits on a slide, on the next slide. So again, we're assuming that we've already established that from the underlying welfare maximization problem, there's no good non-deterministic protocol that figures out whether the welfare is high or whether the welfare is low for some alpha. And we want to deduce the same impossibility result for simple auctions. So let's proceed by contradiction. Okay? So suppose it's hard to differentiate between welfare at least W and welfare at most alpha times W. Alpha is maybe a half or 0.01 or whatever. Okay? For contradiction, let's actually assume that there existed a simple mechanism, okay, so sub-doubly exponential number of actions, with price of anarchy rho strictly better, strictly bigger than alpha. Okay, let's deduce a contradiction. We're going to deduce a contradiction by exhibiting, from this assumption, exhibiting a non-deterministic protocol which does not use very long proofs and actually does differentiate between the high and low welfare cases. Okay, that's what we're going to do. So what does this protocol look like? So again, somehow this is kind of a weird thing we're trying to do, right? So from an assumption about the existence of near-optimal equilibria, we need to extract a non-deterministic communication protocol. Okay? Remember, equilibria are not defined constructively. Right? So this is why it's sort of weird, perhaps, or unintuitive, that impossibility results for a protocol or an algorithm would have anything to do with equilibria. Right? Equilibria, it doesn't come with a constructive, it's a non-constructive definition, seemingly. Okay? Yet, from the assumption, just the assumption of existence of good equilibria, we'll be able to extract a non-deterministic communication protocol which is too good to be true. All right, so suppose our n players have their private inputs. They have their VIs. Either there exists an allocation with welfare at least W, or every allocation has welfare at most alpha times W. They're responsible for figuring out which is the case. Or rather, a prover is responsible for convincing them which of these two are the case. Okay? So what's the protocol look like? That is, what does the prover do? What does the prover write down? Okay? So the prover just writes down a description of an arbitrary approximate Nash equilibrium. Okay, not an arbitrary one that has a short description. Okay, so we want the proof length to be short. Right? So we've ruled out, right, the hypothesis rules out proofs that are too short, so we can get a contradiction by having a short proof. So pick an arbitrary epsilon approximate Nash equilibrium that has description length as small as guaranteed by the sampling argument on the previous slide. So remember, that's polynomial in the number of players in 1 over epsilon, and logarithmic in the number of actions available. If we started with a simple mechanism, so the number of actions, capital N, of each player was sub-doubly exponential, then when we take the logarithm, log n, that's going to be sub-exponential, okay, qualitatively less than 2 to the m. The number of actions was qualitatively less than 2 to the 2 to the m. The number of actions that they randomize over in this equilibrium is qualitatively smaller than 2 to the m. So the description length of this equilibrium, if we started with a simple action, okay, if the action spaces were sub-doubly exponential, then the description length of this approximate equilibrium will be sub-exponential. Okay? All right. So that's what the prover writes down. Okay? And the prover, I guess, also writes down, you know, what is the expected welfare enjoyed by each of the players in this alleged equilibrium. Okay? So what do the players do? Well, so the players, so here's another crucial point, which is that to check something as an equilibrium, okay, so remember, the prover, for correctness, the prover can't be able to trick the players. So the players have to actually check this alleged proof. To verify that it's an equilibrium, the players do not need to communicate at all. Right? You just need to check the best response conditions, which refer only to a single player. So if I'm player number 1, I say, well, let me look at what this prover says I should be doing in this epsilon approximate Nash equilibrium and what it says other players will be doing in it. And now let me just verify that, in fact, I am indeed randomizing only over approximate best responses. I can do that without communicating with anybody else at all. So all players privately check their own equilibrium conditions. They check that the prover did indeed write down the expected welfare they enjoy in this equilibrium. And at that point, all of the players know exactly what the expected welfare of this approximate Nash equilibrium is. Okay? We're not done, but that's really a key step. So the prover writes down an equilibrium, the players can check it is an equilibrium, and the players can check what the welfare of that equilibrium is. How do they use that information? Okay, so how do they decide? Remember, what's hard is to figure out whether the optimal solution is high or the optimal solution is low. And all we know is an equilibrium. But if we assume that the price of anarchy is good, is close to 1, there can't be that big a difference between the welfare of equilibria and the welfare of an optimal solution. And that's what's going to drive the rest of it.
I know only my valuation and know the strategies, then how do I know general welfare, not only mine?
So the prover is going to write down on the blackboard so it's going to say, player 1, I think that you get this welfare in the equilibrium. Write that for player 2 and player n. So now as a player, I just sum up what the prover wrote down on the billboard. So the prover,
Why do I believe him about other people?
well, they're responsible for checking that it's correct for them. Remember, so all of us have to accept the proof. So if the prover tries to violate any best response condition, tries to cheat on having equilibrium, some player will catch it, and that's good enough. If it tries to lie about someone's welfare, that player will catch it, and that's good enough. Yeah. Okay, so hopefully we all agree that the players are now in a position to know what the expected welfare of this approximate equilibrium is. How do they use that information? Well, so first of all, if the welfare is high, okay, if it's bigger than alpha times W, then we're done. Okay? We can't be in case 2. The optimal allocation is only better than this equilibrium. So if even the equilibrium is strictly higher than alpha times W, clearly we're in case 1. We're not in case 2. Okay? But this is the uninteresting case. Okay? Remember, convincing people that welfare is high is always easy. You just write down the allocation. So what would be hard is understanding when you're in case 2. So suppose the expected welfare of this equilibrium is actually at most alpha times W. Okay? This is where we use the assumption that the price of anarchy is sort of too good to be true. Okay, that is rho. Okay? So this equilibrium is not very good. Expected welfare at most alpha times W. How good could the optimal allocation be? Only a 1 over rho factor larger. Okay? Because every equilibrium has welfare at least a rho fraction of the optimal. The optimal can only be a 1 over rho fraction better. So from this upper bound of alpha W on the equilibrium, we get an upper bound of alpha over rho times W on the optimal solution. We've been assuming that rho is bigger than alpha, so this is strictly less than W. So the players then are completely convinced that they can't be in case 1. Okay, they'd have to be in case 2. Okay? So again, what's sort of the, the punchline, the one-line summary of what happens? Our lower bounds say that it's hard to convince players that the welfare is small, okay? But a price of anarchy bound that's too good to be true allows you to convince players of exactly this fact. You exhibit an equilibrium, and that's a good enough proxy of an optimal allocation that if the equilibrium is bad, you know the optimal allocation is also bad. So an equilibrium constitutes an easy-to-check certificate of an upper bound on what the optimal welfare could be. That's exactly what we assumed was hard to do. Is there a question? Or?
The question was what is rho, but I guess I've already read it on the slide.
Yeah, rho is just any number bigger than alpha, so for contradiction. Yeah.
Could it be case 1 rather than not case 2 and the same for the bottom box?
Yeah, so if you like, you can have this be so not in case 2. And this could be so not in case 1.
Which are logically somewhat close.
I agree. Yeah, I agree. If you believe, like if the players believe they're in either of these two cases, which they can't check, but if you believe you're in one of these two, then that's when this would be true. Yeah. Yeah. Then what?
I wouldn't refer about pure math.
Right.
I don't think that actually
So the theorem is going to be false for pure Nash equilibrium. So basically, it's weird. So the price of anarchy with pure Nash equilibrium, there's some ambiguity about how to define it. In general, if an equilibrium need not exist, it's not totally clear what you're talking about when you talk about the price of anarchy. You could, if you like, say, well, let's have bounds on the pure equilibria when they happen to exist. But in simultaneous first price auctions, usually they won't exist, but if they do, they will actually be fully efficient. So they will actually bypass this bound. And so in some sense, somehow thinking about an equilibrium concept which doesn't always exist, you wind up kind of cheating. So kind of exactly the markets where it's hard to find a good equilibrium, the pure are just going to sort of vanish completely. So it's important for the proof. So I mean, another way of saying it is, I said, what does the prover do? The prover writes down an equilibrium. For this to be a well-defined protocol, that equilibrium has to exist. Okay, so that's sort of what's driving this. There's two things which drive this result. One is the guaranteed existence of the equilibrium concept. Secondly is the fact that the players can privately verify the equilibrium. Yeah. Other questions?
At some point yesterday, someone brought up second price auctions.
Mm-hmm.
Second price auction equilibrium always exists.
Mm-hmm.
You said something about the bounds being, the results being similar, but there you get an exact equilibrium.
So say it again. Second price auctions
The equilibrium always exists.
in the multi-item for simultaneous second price auctions, or for simultaneous second price auctions, or
Yeah.
yeah, I think it depends on the assumptions on the valuations. So I think if you impose some restrictions on the valuations, I agree. There's guaranteed existence of pure Nash equilibrium in simultaneous second price auctions. I don't think that's true for general valuations, if memory serves.
With
Which option are you
So-
talking about? I mean, you have here those 2 to the n bundles.
I was thinking of something.
Yeah, subadditive, right. Yeah, agreed. Yeah, then you start getting it. Yeah, exactly right. Yeah, yeah. Right, so then if you do have so good question. So the question is, well, sometimes you will have guaranteed existence of pure equilibria, and then actually this exact same proof will work, will apply. So the first price auction case, pure Nash equilibria can cheat. In the second price subadditive case, they can't. Yeah, good. Yeah.
When this proof works, you actually get the proof is about the actual pure Nash, not about the
Yes. So Amos's point is that you don't have this description length problem with pure Nash, because you just write down a single strategy for each player. So the epsilon, that's a good point. The epsilon goes away for the pure Nash case when you have guaranteed existence. Yeah. Okay. Let me wrap up with two open questions, very directly related to these lectures that are very juicy. I mean, I guess one question, one sort of direction which I didn't put on this slide. So, what in some sense is the takeaway from these lectures? I hope the takeaway is that, there are tools which are perhaps unfamiliar to an economics graduate student, who's just been taking the microecon core, for example, but yet, come from computer science, as it happens, and yet are sort of perfectly suited for making statements which I think are of basic economic interest. I showcased these connections in this one particular setting, multi-item auctions and approximate welfare guarantees, which I think is interesting, but this really should just be the tip of the iceberg, right? There should be many other basic questions of economic interest where, for a number of reasons, perhaps the optimal solution is just impossible to deploy, like the VCG mechanism here. Perhaps it's just analytically too complicated to understand, like say in multi-dimensional optimal mechanism design. For whatever reason, approximation is kind of the trick which allows you to dodge the traditional barriers to making progress and salvaging statements which are really, I think, pretty meaningful about economic applications that many of us care about. So that's kind of not a concrete open question, but that's really what I hope the students in the audience maybe remember from these talks weeks or months from now. Okay, but for those of you that like really concrete open questions, where it's just they're either true or false, here's two of them. Yesterday we talked about price of anarchy guarantees, so positive results. We talked at length about first price auctions, and it probably felt like we mostly had tight results. Okay, we had best possible guarantees. Like we had this 63%, we had this bad example for first price auctions, and then we had this matching upper bound, even in the multi-item case. But I want to point out that if you recall, this was the lower bound with 3 bidders, and one was deterministically won, the rest were equal. That was a correlated private values model. Okay? And in an auction theory course, usually you spend most of your time on the independent private values model with first price auctions. So how inefficient can first price auctions be in the independent private values model? We actually don't know the answer to this utterly basic question. Okay? We know we have a positive result of 63% even for the correlated case. So the question is there a construction that meets it that just uses independent valuations? The best construction we know is quite far off, something like 87%. And I actually have very little intuition about what the right answer is. So here's a very basic question that it would be really nice to know the answer. You also may have noticed my sleight of hand where yesterday I was talking about submodular valuations because it was convenient for my story then, and today I seem to talk about subadditive valuations. Why was that convenient for my story today? It's because we actually do not know the optimal simple auction for submodular valuations. We do know it in a few cases. It's not just subadditive. But for the submodular case, we actually do not know the answer. Okay? One thing we do know is we know a precise analysis of exactly how good simultaneous first price auctions are. As we saw yesterday, we proved a guarantee of 63%, and actually that can be met. Okay, that same paper by Christodoulou et al. Give an explicit construction showing that there is a valuation profile of submodular valuations. There is a Nash equilibrium that's off by 63%. So for that specific auction format, we know the correct answer. Again, can we do better? Is there some other smarter but still simple mechanism which beats 63%? Now from today's talk, you should say, oh, well, probably not, and all we need to do is prove a communication complexity lower bound for the special case of submodular valuations. Right? So we had the subadditive one that said for all alpha bigger than 1/2, you couldn't do something. So now we just need an analogous statement for all alpha bigger than 63%. You can't differentiate between the high and low welfare cases. Problem, that statement is false. Okay? For submodular valuations, there actually is a communication protocol which just uses a polynomial amount of communication that beats the 63% barrier. Okay? So that fundamentally limits what kind of impossibility results you could prove on simple auctions for the submodular valuation case. Okay? So that leaves us with exactly 2 possibilities, each of which would be extremely interesting, in my opinion. So answer 1 would be that there actually exists a simple mechanism that outperforms simultaneous first price auctions for submodular valuations that beats 63%. You can use the communication complexity techniques to show that you can't do better than 77%. Those of you keeping track, this is 1 minus 1 over 2 times E. But we don't know where we are in between. So that would be really interesting. Some different, possibly novel auction format beating 63%. The other possibility is that 63% actually is the right answer. Simultaneous first price auctions actually are optimal, But then to prove that, you would necessarily have to invent techniques beyond the state-of-the-art ones that I've shown you today. So either of those would be a terrific resolution of that problem. And with that, I'll conclude my lectures. Thanks very much.